So hello everyone, and I and Akanksha would like to welcome all of you to this new course that we are starting from today, Design and Detailing of Composite Structures using ETABS plus Idea Statica plus Manual Calculations. So this is the session 1 that we are starting from today, and uh, so I'll take you through we will discuss using a small presentation today because there are some topics that I want you to understand before we begin. So all of you will be on mute and you will not be able to turn on your videos also. So if you want to communicate, you can put in your queries or comments or whatever you want to say through the chat box. So the chat box is going to be continuously monitored, and using the chat box, we'll be able to read and reply to your queries or comments or uh, other issues. I'll also request you to join with your full name so that you can be identified in the live session. So let us begin. I hope you can see the screen and you can see the presentation slide that has been shared, and you can see my face and listen to my voice. Okay. I hope I'm audible. Good. So let us again quickly see why we want to learn composite structures, okay, and how this course will help you. And I'll just quickly take you through the details of the course. These three things we had covered in the introductory session also, but just a quick recap of what we had done. And then we will look into the different composite structural systems that we are going to cover in this course. Uh, the two stages in composite design that we have to take care, that is the construction stage and the composite stage. What are our codes and which codes we are going to study, and then we will go through, or this we won't be able to start in today's session, but in the coming few sessions we will discuss some basic concepts of analysis and design before we move ahead with the course, because these will be your, let's call them as the building blocks for the course. Okay, so this will help us in the course later on. So I thought we will cover these things at the onset or at the beginning of the course itself. So this is what we are trying to cover today. I think we'll be able to cover till this point, and from here onwards, some basic concept onwards, we will start from the next session. So you all know that what is composite. So here we are not talking about laminar composites. I think, I don't know if you know it or not. There are laminar composites also. Have you heard about laminar composites? So laminar composite would mean, for example, a plywood. How many of you have seen plywood furniture? I think all of you have seen plywood furniture. So there is one ply, yeah. Then there is another ply. Then there is another ply, isn't it? So what we do is that we take all these plies, then they are to a certain thickness, whatever we want. And in between the layers, how are they connected together in between the layers? So they are joined through, anyone? They are joined through some glue or adhesive. Okay. So they will be joined through using some glue or adhesive to make one plywood. So this is one ply, this is ply, this is ply, and this is ply. And then this will be a glue or adhesive, and these are pressed to form one plywood. So these are called as laminar items. Okay. Similarly, you may get laminar out of carbon fibers, or you may get laminar of different out of different materials. In fact, when you see your aeroplane bodies, or if you see FRP structures, many of them are laminar composites. So here we are not talking about laminar composites. We are mostly, I mean, we are going to talk about the composite where we are joining together the RCC and structural steel. And why do we do that? To to get the best of both the materials in terms of strength and stiffness. Okay, you know all these things. And now you know that with the rise of structural steel construction in industrial, in residential and commercial projects also, the composite construction has also started happening at a greater rate. So just I think, yeah, couple of days ago I was interacting with one participant who is doing a composite building in Mumbai, and there uh, so he was looking after the project management part of it, but it was a multi-story commercial building that was using composite slabs, deck slabs, with composite beam construction and composite columns also. So you will see that these things are now gaining prevalence, and because steel structural construction is gaining prevalence, composite will also be used more and more. And of course, it's not covered in our undergraduate or postgraduate courses. However, IIT Indore has a course in composite design at the postgraduate level. So, IIT Indore is teaching composite designs to its postgraduate students, MTech structures. Yes. So, but still, I don't think any other institution or uh, any other institution has such a course that is running or which they are conducting. So anyway, so that's why, in spite of their obvious importance, these types of courses are not found or not available, and therefore many of the structural engineers are forced to learn on their own. In fact, till the 2002 version, we didn't have a codal support also. So codal support was also lacking, because which is the Indian code we are going to use? Anyone remembers the name? So the Indian code that we are going to use is IS11384, which was revised in 2022. Okay. So this was recently revised, you can see, and it was not just a revision, but it was a major upgradation that happened. So it was a major upgradation that was carried out. Before this version, 2022 version, the version before this was, anyone? Is my voice audible? Can just someone confirm? Yes, no? Quickly. And can you see the screen? And my voice is all good. So thank you. So the major before this, which was the version that was prevalent, or which was the version in force? So it was the 11384 1985. So 1985 was a very, I would say, uh, a very basic level document, only 10-12 pages long, without any calculations or without any proper coverage of different structural composite elements. So till 2022, you only had this code available. This 2022 code is just what, 3-4 years old, and still many of the structural engineers are not uh, acquainted with this code properly. Okay, so I would say that codal support was also lacking. Even your software were not updated enough. However, now ETABS does has the 11384-2022 design module updated in it, and I heard that STAD has also introduced a composite design module in its uh, programming. Okay, so now STAD also has it. ETABS has been having it for the past couple of years. So the codal support was also not there for the structural engineers. But now, with the advent of new code, we are in a more comfortable position. And the structural engineers who are looking to go to the next level, for them, it is important that they should be able to understand and use composite structure in their projects. Okay. So this is going to be our effort in this course, to enable the participants to learn and use composite structures, composite designs for their actual projects or for their work. So through this course, we will be learning these codes, and I have already, okay, about this I'll talk later. So we are going to cover 11384 because the 11384 is largely derived from the Eurocode 1994 part 4, okay, and Eurocode 1994 part 3. So because it is largely derived from the Euro codes, if we are studying the Indian code, in effect, we are also covering the Euro codes, isn't it? And then we will also go through the chapter I of AISC 360-22, that is the American code, wherein we will cover the composite structures. So why are we doing one course where we are covering both the codes? Because if you see, there is not much given in AISC 360 in terms of design procedures or design steps. Very little information is given. Okay. So there is no point in having a different or separate course just to cover AISC 360 where nothing much is given as such. So therefore it makes more sense, and therefore we thought that in one course itself we should cover both the Indian as well as the American code. And in the process of doing Indian code, we are anyway covering the Euro code also, because Indian code is largely taken from the Euro code clause by clause, word by word. Okay. So in this way, I think this course will give you a comprehensive, in-depth understanding of all the different country codes, and you will be able to use different country codes for your composite design. We will also be doing a lot of manual calculations as we always do. Okay. And the good thing is that ETABS is able to do all these things for us. So every time we may not need to do manual calculations, we can rely on ETABS. And for connection design, we will have some discussion on Idea Statica also. And in this course, we will also take two projects. One we will do using the Indian code, one using the American code to apply the learnings. So these are the different things that we are going to study and discuss. We have covered these aspects or these points in the introductory session also. So I'll just quickly go through it. That what are the things we are going to cover? Understanding different types of structural systems. So we are going to start with this in today's session later on. Okay. Understanding shear interaction, very important concept. If you understand this concept, I think the composite design is over. That means most of the things will be understood if you properly understand the shear interaction uh, effect and what is the meaning of shear interaction. So therefore, I have included this before starting anything. Then we will go through the important limit states of strength and serviceability and fatigue for construction stage and composite stage. These are the details. These are the topics that we are going to cover in this course. Just a quick highlight. Then we will go to the philosophy of composite structure design and which materials are used, their properties, their characteristics, understanding different loads and load combinations, analysis procedures that we have to use. Then we will go to clause by clause understanding of both these codes. Then we will start with composite beams, design and detailing. So these are the different topics we will cover. Then we'll go to shear connectors, different types of shear connectors. Then composite slabs. Okay, these are the various topics we will cover in composite slabs. Then composite columns. So what are the different types of column configurations used? What are the different checks we need to do for columns? All those things we will cover. And then we will look into the connection design for composites. And finally, we will take two sample projects. And as I told you before, we will be referring to 11384, that is the Indian standard. Then the Indian concrete code 456, Indian steel design code IS 800, the American code AISC 360 chapter I, and if required, we will refer to some provisions of the American concrete code, that is the ACI 318. And the software we are going to use is ETABS Idea Statica Excel. Good. So now let us begin with the different composite structural systems. How many of you have used composite structures in one way or the other in their projects? Although they may not be knowing the design and detailing principles, but they have used some of these things in their projects. Or if they have not directly used, they have seen some projects where such elements were used. Yogita ji is saying she has used composite structural systems. Uh, Deck slabs have been used, is what I am understanding. I think most of the people must have used deck slabs in their project. If especially you are doing some structural steel projects, multi-storied structural steel frame projects or warehouse projects, usually you would see a mezzanine slab, and then in that mezzanine slab, they would have a deck sheet, deck slab, and on top of that deck slab, there will be concrete topping, and then that deck slab will be resting on steel beams. I think many of you might have used such elements in their project work. I'm not saying you understood or you understand the design behind it, but at least you have seen its use or you have used it in your projects, isn't it? I think in India right now, the most common application is deck slabs, where we use deck slabs with concrete topping. That is the most common application that you will find. Okay. So yeah, that is also a form of, or that is also a type of composite structural system. But let us see which are the different types of composite structural systems that we are going to discuss and cover. So composite beams, shear connectors, composite slabs, and composite columns. So these are the four structural systems that we are going to mainly focus on and that we are going to cover in this course. Let us see one by one each of them. So what is meaning of composite beam? In this, essentially, first of all, the first thing you need to understand is that there will be RCC plus structural steel. Okay. In composites that we are going to discuss, important point is in composite systems that we are going to discuss, it is more to do with structural steel than with RCC. Do you get this point? Composite systems are more of structural steel than RCC. What I mean to say, what I am trying to say by this is that it's not a 50-50 participation, or it's not as if both of them are equally important. In composite systems, the structural steel member is the dominant partner, okay? And the supporting role will be played by the concrete that you put into it. Is this point clear? So when I say composite beams, essentially what it means is that there will be a basic beam. That basic beam will be of structural steel section. Okay. Are you able to see this I-shaped beam? Hello. So this is my structural steel beam, two flanges, one web. Now in normal course, this would be my, let's say, a normal steel I-beam. Okay. Now if I were to put a slab, an RCC element on top of it, if I were to put an RCC element on top of it, let's call this as RCC slab. Okay. And if they were to act in unison, if they were to act as one unit, if I want them to act as one unit, then this becomes an example of what? Tell me. This becomes an example of, hello, anyone would like to say? So this becomes an example of a composite beam. Is it understood? This becomes one of the most commonly found examples of composite beam. So I had a beam, normal I section beam, structural steel beam. On, let's say, top of it, I put an RCC slab. Somehow I connected these two elements together, which we will discuss later on, of course, how I am going to connect them together. So let's say somehow I was able to connect them together. Now the total unit that I get, I call it as a composite beam. Okay. Another example of composite beam can be, so this is the composite beam with solid slab. Another example could be that instead of using a solid slab, I use what? I use a deck slab. What is the meaning of deck slab? I'll just show it to you in the next image that follows. But just to show you, okay, this deck slab thing I'll tell you in the next slide because I have an image over there. If I were to put my concrete, although it's not very common, but if I were to put my concrete like this over here, then this becomes an example of what? Suppose I was to put a formwork and fill concrete, and if this was the resulting beam that I got, so I have this I beam, and then these elements I have put concrete. So this will be called as what, anyone? Hello. So I can call this as partially encased beams. Is it clear? This is my concrete. This is my structural steel. So this I will call it as a partially encased beam. If I were to use a section where I had a larger RCC element like this, and inside it I put a beam fully encased inside, then this type of section I'll call it as what? So this is complete RCC and sort of I section beam has been put completely inside it. This will be called as what? If this was partially encased, this will be, this is simple to answer. Fully encased. I hope you are getting it or it's not clear. Simple terms, I guess. Fully encased. Yeah. So this becomes my fully encased beam. So partially encased, fully encased. Then if I were to use a hollow section, now see what I have done. I have changed the steel shape and it is a hollow section. So this forms the outer covering. This is, let's say, a rectangular hollow section. So I'm calling it as RHS, rectangular hollow section. Now inside it, I fill it with concrete. And this cross section was to act as a beam. So this becomes what? What I will call this as filled composite beam. Is that clear? So are we clear with these different terms? So one can be a composite beam with solid slab. In composite beams with solid slab, as I explained, there will be a I section and on top of it, there will be a slab that we have, and then that slab and I section or whatever structural steel section you are using are acting as a composite system that we are calling it as composite beam with solid slab. Then I told you another type could be where we are sort of encasing my beam inside, encasing my beam inside concrete. I'm calling this as partially encased. And if I were to fully put concrete and embed my beam fully inside it, I can call it as fully encased. And if I were to use some hollow section and put concrete inside it, of course, this concreting of this thing will be difficult, isn't it? I hope you are able to imagine if I was using this RHS as a beam and if I were to fill concrete in it, can I fill concrete from top in this case? Hello. Would I be able to fill my concrete from top? Imagine that I wanted to use this as a composite beam. Okay. So I used a RHS. So this RHS is like this along the length. This entire tubular section is there. So will I be able to fill from top? No. Will I be able to fill from these sides? No, because there is a wall of RHS over here. So the only place from where I have to fill is the horizontally, I have to fill it inside. You understand? So that is slightly difficult process of filling. I have to do a horizontal filling. I hope you are able to imagine this thing. Alright. If I have a beam, see the L section. Let's say this is my L section of the beam. This is the beam span. Suppose it was a 6-meter beam. Okay. I place the hollow section. This is open from only the starting and ending point. So if I am doing RCC, cast in situ RCC, I have to put somehow fill the concrete from here and push it inside. Okay. And then push it inside. But then the vibration and I mean, using a vibrator over here or the compaction consolidation we cannot be assured of, because if it's a 6-meter span, I don't know how well the concrete is getting compacted. So at best these types of things can be used as a precast filled beam. You get my point what I'm saying? Instead of doing cast in situ filling for this, a good way to use these filled composite beams would be that you use them as precast. That means, let's say you had this hollow section, you cast it first in workshop or wherever. That time you do a vertical casting. That means you cast it from here, and then once this piece is ready, then you just put it on site wherever required. You got my point? So this can be one of the way of using an RHS or a filled composite beam on site. Otherwise, for partially encased or fully encased or composites beams with slab, you can do easy filling. Dr. Saab is saying, I hope it is Dr. Saab, Vinu Bhai Saab. He is saying can be filled with self-compacting concrete. Yes, sir, it can be filled, but then you will not be able to ascertain whether the concrete has been filled properly or there have been some honeycombs left, or how well it has reached all the places and corners. We will not be able to ascertain that, especially if your spans are, let's say, 5-6 meter beam span and you were to fill it from starting and ending. I don't think you will be able to ascertain that adequacy of filling or how well it has been filled. So in my opinion, if you want to use filled composite beams, it is better to use them as precast. That means you cast concrete, bring a piece, bring a ready-made piece where concrete has already been cast, and then just put it on site. That is my opinion. Okay. Or else you may cut slots from top. Another way could be that you cut slots at the top, fill concrete, and then weld plates again. I think this can be another way that you can think of. Anyway, so these are the different types of composite beams. Now, normally you will see, so I, sorry, yeah. So I think you understand this composite beam with solid slab, you understand encased composite beams, and I guess you have understood infilled composite beams. Encased can be partially encased or fully encased. Now, most of the Indian standard that you will see focuses is focusing more on this. Indian standard, if you see, is sort of focusing only on this composite beams with solid slab, composite beams with deck slabs. That means where you have a beam and on top of it you are putting the RCC slab. Now that RCC slab can be in the form of solid slab or deck slab filled with concrete. But the Indian standards are only sort of focusing on these three items. But then we may also want to use encased and infilled beams. So there are no ready-made, I would say no ready-made formulae available, directly available, no ready-made formulae directly available in Indian code as such. But we will use or we will discuss the design of these beams also through easy jugards. Okay, we'll discuss these beams also, although these beams are not explicitly covered or independently covered in 11384, but through some easy jugaad, we will discuss these beams also. Understood? Just yesterday, I was listening to Professor Abhay Gupta sir, where he gave a good idea while discussing that actually many of you have faced this difficulty and have asked this query to me also and on other forums also. And I was not able to give answers earlier, but now I think I have a good answer for this. Suppose this is an elevation, okay? This is an elevation, and these two are your shear walls. Okay, you are making an RCC building. These two are shear walls. I'm showing you a elevational view. So these elements through which we connect these shear walls, these are called as what? Anyone? These elements, let's say at floor levels, we connect these two shear walls through an element like this. What do we call this as? Correct. Yes. So as Mr. Hasinul is saying, we call them as spandrels or coupling beams, isn't it? Now, in case of spandrels or coupling beams, what is one design problem that you must have faced? And this just struck me yesterday. Yesterday night, I was listening to Professor Abhay Gupta sir, where he had raised this point, and it just struck me. Yeah. So, what is one problem that you face in spandrels or coupling beams? The main problem that you face is that the shear demand on these beams is very high, isn't it? Shear demand is very high. Shear demand is very high, because of which you often get very large sizes for these coupling beams. So what if in this coupling beam, anyone got the idea what I'm going to say now? What if in this coupling beam, and many people or many consultants in India and abroad have been doing this exercise or have this practice. So it's nothing new that I'm telling you, but just the maths behind it, it struck me yesterday. So if you were to look in the section AA, because shear demand is a problem for this coupling beam design, many of the consultants, what they are doing, that they insert a I section or webs in this. Have you seen such thing? Anyone has seen such thing? So there is an I section inserted in this coupling beam. Okay, that means I section will be inserted along the span. So this along this span, the I section will be inserted just like a beam. So your outer reinforcement will be like this. This becomes your outer reinforcement of your coupling beam. And these are your lateral stirrups. And then you also have a I section inserted. So this I section will help you to take the flexural demand and shear demand, which your reinforcements were not capable of taking, or you required very large sizes or whatever. So to take care of that, if you put an I beam, so I was often asked this question that how to design this type of section, but I think now I know the answer, that this section can be a type of what? We can find the shear that this can resist and the bending moments that this section can resist through the concept of what? It is similar to which of these types? Hello? Which of these composite beam type can I refer to? So this can become a fully encased. I was expecting someone to answer this. This can become a fully encased composite beam, yes or no? And I can apply the same principles of fully encased composite beams over here. Good. So just yesterday night, this answer struck me, that this doubt that many of us often have, that what is the mathematics behind this. I think now we can do this work whereby we can design this as a fully encased composite beam and find out the shear and bending moment capacities, and then accordingly design this. Anyway, good. So we will be discussing all these types. Now the two types that I did not discuss were the composite beams with deck slabs. So I'll just take you to deck slab photo All these images have been taken from the internet. So this is a typical composite beam with solid slab cross section that you can see. Below is an I section. On top of it is a solid slab. Yeah, one more point. Till now, you just saw that I was always drawing an I section and I was showing slab connected to it, isn't it? So can I not have any other section instead of I section? You saw I was always drawing this I section as the structural shape, and then this was my RCC slab. Even for encased, I was drawing an I section. So can I not have any other section type? Of course, for RHS, of course, for RHS, it has to be a closed section. Inside it will be concrete. But for encased and beam on beam with solid slab on top of it or deck slab with top of it, I was always drawing this I section. So can I not have any other section type is my question. So yes, I can of course have other section types. So even when I was making an encased section, I was drawing an I-shaped beam and then encasing it inside concrete. So can I not have any other section type? I can have. Uh, I may have an RHS or a closed box section also like this. And top of it, I can have a solid slab attached. The problems, however, are what? Problems, however, can be one is of proper shear connection. One is of proper shear connection in these cases. Okay. In your I section, it is easy to properly shear connect it. Mr. Hastinul is saying web capacity. No, you can get good web capacity in hollow section also. In fact, there are two webs over here. Instead of one thick web, there are two webs over here. Web capacity is not a problem. Shear connection sometimes can be problematic. Also, if you are using this as an encased beam, suppose you had two options of encased beams. So you had encased beam like this, and you could either use a hollow section encased inside, or you had the option of using an I section. So which of them would you prefer and why? Any thoughts? Suppose I was to use an encased section. Hello. And this is an encased. That means outside is concrete and I am uh, putting a structural steel shape inside. So amongst this A and B, which of them would you prefer? Fully encased beam. Yes, please. Siddhakala is saying I section will cater more concrete. Cater means I'm not sure what do you mean by cater. Have will have more concrete. So we can see it will have more concrete. So see, in my opinion, I guess in my opinion, the encased section with I-beam will be a better option. In my opinion, this encased section with an I-beam will be a better option because this is providing you more surface area for the composite action to set in. You understand this point? This will provide or this will allow for the composite action to better set in because of the larger surface area that you are having between concrete and steel surface. Okay. So because of that better composite action, you will be able to have better moment capacities of this full cross section. Clear? So this is my opinion, although I could not find such a reason in the books, but just because of the shape that we have, this is my understanding. All right. So most of the times you will see that in encased beams, I section is the preferred section type. In infilled beams, of course, it has to be a closed section. So it will be a rectangular hollow or a square hollow or circular pipe. And in these cases, where you have a composites beam, where you have a steel beam with an RCC slab on top of it, you can have I section or any other section type also. But for easy connections, we prefer I sections over there. Easy connection means easy connection between slab and beam. We may prefer I section over there. So is this clear? What I have just said? Is it understood? Okay. Although there is no such codal restriction, you can use any structural shape, but mostly you will find that the Indian code covers I shapes for these types of beams, and the American code gives you the option of uh, both. That means you can use an RHS also and I section also, but Indian codes mostly give you the choice of I sections. Mr. Asinul is saying in case A, concrete is also inside the RHS. Now that you will not be able to ensure, right? Because you are filling from the top. If you are doing a cast in situ filling, you are filling the concrete from top. So concrete going inside, you don't know how much of concrete is going inside, how well it is going inside. So that we are anyway not considering. Understood? Okay. So good. So now I hope this preliminary discussion is clear. So just to summarize what I just said, mainly in codes you will see Indian standards focusing more on these three types, but we will discuss the encased beams also and infill beams also through some easy jugards. Basically what is the jugad that we are doing? Nothing very hi-fi. We will use the flexural capacities that are given for these types of. Okay, I'll talk about this after 10-15 minutes. Wait. You yourself will get idea. Now I'll just explain these two types, deck slabs, and what is meant by ribs parallel to and ribs perpendicular to. So let me just explain that to you. So this was an image of solid slab. Now this is an image on your right side, which is a very popular image, which you will, I think, see everywhere being used whenever a topic of composite structures comes up. I think this image was originally given in the Eurocode, and then this image was picked up in the book by R.P. Johnson. R.P. Johnson is a very good book, okay? You should go through it. It's a very detailed and good explanatory book. I'll provide you the PDF and you can study that. You may take a printout if you want, but it's a good book to study. Composite design. The title of the book is Composite Structures of Steel and Concrete by Professor. I don't know whether he was professor or not. Yeah, professor. Professor R.P. Johnson. Composite structures of steel and concrete. Okay. In fact, in our Indian code, some of the lines have been directly picked from this book, word to word. I'll show you some lines in Indian standard which have been picked line to line, word to word from this R.P. Johnson's book. So go through this book. I will upload this PDF. You may take a printout of it. So I was saying that this image was first, I guess, shown in the Eurocode, and then it found its way in the book also. And now I think this image is one of the most popular images that you find on the internet when it comes to composite beams and composite slabs. So instead of using a solid slab, if I used wait a minute, just see if I have good images. Okay, wait. I'll explain a few things. Are you able to see this whiteboard? Yeah. So see, understand one thing. Let's say I'm drawing a plan view. I'm drawing a plan view. These red items are my beams. Okay. These red items are my beams in plan. And let's say these were my columns. Don't worry about what column it is, whether it is composite column, RCC column, infilled column, encased column. Don't worry about that right now. So you know this load transfer path. It's very easy to understand. Load transfer happens from slab onto, let's say, beams onto columns. Now, when you put a slab, either you can put a RCC slab. Okay. Now for RCC slab, what happens? That you need to have a formwork first. So you put a formwork, and then after putting the formwork, you put concrete on top of it and then remove the formwork, isn't it? That's how you fill the RCC slab. Am I clear? Okay. Now suppose, so you put formwork, you put a formwork, then you put reinforcement, then you do the concreting, then you put the formwork, then you put reinforcement, then you do the concreting, then you remove the formwork. Correct? This is the usual process that we follow. So this becomes time consuming. Why? Because you have put the formwork. So putting the formwork will take you some time. Then after doing the concreting, you cannot remove the formwork immediately. It has to be removed after the concrete hardens and it sets in and gains strength. So there is a 7 day or a 14-day cycle depending on spans and all those things. So this thing takes time and it slows down your overall work progress, isn't it? Now sometimes it is also difficult to put formwork if you are at greater heights. Suppose I am now trying to show you an elevational view. So suppose this was my structure. I'm showing you an elevation, okay? So these are all my columns. Now here there were slabs. So I was maintaining a 3 feet height, sorry, 3 meter height, let's say floor to floor. But here I wanted to have a double slab, double heighted slab. Let's say I wanted an atrium. Now if I were to cast this slab, the problem would be that I will have to bring formwork right from double height. Do you agree? I would need the formwork support. I mean, first I need to do props, scaffolding. So these are, let's say, my couplock system. Then I will have to put my formwork over here. Are you with me so far in understanding what's happening? Then I put a formwork. Then I do the concreting. So it becomes time consuming also. It becomes expensive also. This is the scaffolding that I have erected. Yeah. In the meantime, this entire thing is happening. Your space over here is also obstructed. You cannot do anything. Any activity cannot happen over here. Similarly, now if I have to do this slab, let's say this was a triple height. So I have to first erect a triple height scaffolding, couplock system or whatever system yeah, in this case, couplock will be the option. So you will have to go for a couplock system. Okay. Then again, you will have to put your then form work. Then you will have to do the concreting. Again, this entire thing is stuck up. This space is stuck up, so to say. So if instead of this, what if I could combine? What if I could combine the formwork and the reinforcement together as one item? You getting my point? Okay. What if, see, I was putting my form, then I was putting my reinforcement, then I was doing the concreting and removing the form. Now, what if I could combine these two items in one element itself? That what I am putting as a formwork acts as my reinforcement also. Okay, I'm able to do the concreting, and this formwork is, let's say, self-supporting, so I don't need to put any scaffoldings also. And after concreting, I don't have to remove anything also, and I don't need to put any additional reinforcement also, because this formwork itself will act as the reinforcement. So if I want to do this, a good option can be that I use a steel plate. Just understand, I use a steel plate. Anyway, in formwork we use steel plates. We use wooden plates also, wooden forms also, but let's say I used a steel plate. Okay, I used a steel plate. Now I use my steel plate. Then I did my concreting. Then I did not remove my steel plate. So steel plate first acted as a formwork, and then later on, when concrete hardened, it also acted as my reinforcement. Do you understand? But using steel plate is problematic. Why it is problematic? Because steel plate thickness is very small. So because of small steel plate thickness, it will not be able to act as a proper formwork for larger spans, isn't it? You understand? If I'm using just a thin steel plate, if I'm using just a thin steel plate, I'm showing you the cross-sectional view. And now this is my RCC slab. This is the if width of the slab, let's say. This is my steel plate. So I am using this as a formwork. And I want this to act as a reinforcement also. The problem in this is that this steel plate is so thin that its moment capacity about its axis of bending will be very, very small. You understand this point? Hello. The steel plate in itself is so thin. I'm using, let's say, 0.8 mm or 1 mm or 2 mm, 2 mm, 1.2 mm. That's it. The steel plate is very small. I cannot have such a small, thin steel plate being used. If I want to go beyond, let's say I want to use a 6, 7 mm thickness plate, then it does not become cost effective. Then putting a scaffolding and putting a reinforcement is much more cheaper than putting a 6 mm steel plate as a formwork and reinforcement. You get my point? So instead of using this type of a plate, if I wanted to enhance the moment carrying capacity, what I could do? Any ideas? If I wanted to use a steel plate, I did not want to use a thin, did not want to use a thick steel plate, but still I wanted to enhance the moment carrying capacity of that steel plate. What is my good option? That I use it as a folded plate. You understand? I think you are getting this point. So instead of using a plate, thin plate like this, what if I could form it and instead use it as a formed plate in this manner? Are you with me so far? What I'm saying? Hello. So this is the same thickness, but what I did is the concept understood to everyone. This is very important to understand. See, concept is very simple. What I said is that in my normal construction, I'm using an RCC's, I'm using a formwork, then I'm putting reinforcement, then I have to remove the form. Sometimes to support the formwork, I have to put so much of scaffolding. It's all very time consuming. So I thought, why not to use the formwork and then use it as reinforcement also. Now, when I want to use a normal plate, I cannot use a thin plate because it has a very small moment carrying capacity about its axis of bending. So the moment of inertia that it can offer is negligible. Okay. And if I go on to use a very thick plate, which can act as a formwork also, and which can act as reinforcement also, it does not become cost efficient. So what I do a good trick. I use formed profile sheet. What is the meaning of forming? This is called as cold forming. Cold form. What is the meaning of cold form? That I get my plate from the market, and then in the rollers, I have a roller set. In my roller set machine, in the cold form, that means I'm not raising the temperature of this plate. In the cold temperature or in the normal room temperature itself, I give this type of a shape to the plate. So this is called as cold formed profile. Why profile? Because now I have made a profile out of this, like this sheet. So quite clearly, this will have a very large moment carrying capacity. Do you understand or not? For the same thickness, let's say the thickness remain the same 1 mm, but I will have a very, very large moment capacity that I will get from this type of shape. Clear? So now if I were to use this shape, and act as this shape was to act as a formwork, and then this shape was to act as reinforcement later on, then I call this system as deck slab, profile sheeting, profile sheet deck slab, or profiled metal deck slab. Is this clear now? Quick yes, no? The concept is clear? Okay. In this deck slab, this is usually called as the crest. We'll discuss all these things, but because one of the items we need to understand right now, this you can call it as the trough. Okay. Then there's a pattern that you see. There is this pattern that we will repeat over the width. So usually this can be called as the pitch, where the pattern repeats itself again and again. We can call it as the pitch. And one of the important things is these are called as the ribs. Which are the ribs? Let me show you. Now we come back to the picture, this image. So these are called as the ribs. Can you see these lines that I'm drawing? Hello. These are called as the rib lines. Okay. So you understand these terminologies? These lines along this direction are called as the rib lines. Now just looking at the profile, you need to understand one very important thing with composite deck slabs, that these essentially act as one-way slabs. Whenever you put deck slabs, that is profiled metal decks with concrete topping, they will essentially act as one-way slabs. One-way slabs, I mean to say, okay, if I were to ask you in which direction they will act as one way, I just said they will act as one-way slabs, but in which direction they will act as one way? Okay, I will help you to imagine. Let's say this is the plan view, okay, of your metal deck profile, and these lines that I'm drawing, if you are not able to understand right now, don't worry, because these things we will discuss later on also. But there was one point that I wanted you to understand, so I just thought let me cover it right now. Let's say this is the plan view that you can see, okay. These lines that I'm drawing are the rib lines. If I were to draw a section like this, AA, this AA section will look like this. The profile shape will come over here. Are you able to get it? This is my AA section. I hope you are able to imagine. So the deck slabs, as a couple of you have rightly pointed out, that the deck slabs will essentially act as one-way slabs along this direction, along the rib line. Because along the rib line, if I were to cut a section across it, AA, then this is the shape that I get, and this is the shape where I'm getting the maximum moment of inertia, or the advantage of moment of inertia. I'm able to get it over here. So this deck slab essentially acts as one-way slab along the rib lines. Clear? Is this point understood, please? This is very important for you to understand. Okay. Hello. Okay. Now, having understood this, the manner in which we connect the beams to the deck slab, the manner in which we connect the beams to the deck slab defines, or yeah, defines the design of the beam. What it means is, let's say this is the plan view. Please understand, this is the plan view, and you can see the rib lines. Now I draw a beam. Oppo is saying, what is the Oppo? Oppo, what is your name? Just come in with your real name. Oppo is saying section A should have only two lines, bottom and top. Bottom and top. Question not clear. Two lines means bottom and top means. No, see, these are. I'm not sure about the question. Is everyone able to imagine this section AA? Yeah, see, it's not an accurate section. What you mean to say is that this line will be seen somewhere nearer, then there will be a wider line, then there will be a closer line like this, then there will be a wider line for this. So it's not an accurate section as such, but I'm just trying to show you the representative way. Okay. Perhaps you could share one image, what type of section AA you want. Share it on WhatsApp group. I'll have a look. Or you can attach one image over here also. Good. So now this was my deck slab. I am showing you the plan view. The ribs are going in this direction. Pitch should be shown on section BB, which you have shown in section AA. No, no, no. See, if this is my width, suppose, then this is the width. Pitch will not be on BB. This is the right thing to draw. I think you are confused. I'll show you another image where it will be clear. Just give me a minute. I'll show you one more image. Okay. Now, one very important thing you need to understand, that suppose I were to put a beam over here. This is the plan view that we have drawn. Suppose I put a beam. Okay. These are my beams. Now these beams are having deck slab on top of it. We agree with this statement, of course. These are beams. These beams are having deck slab on top of it. So these composite beams, when we will design, these will be composite beams with deck slab ribs. Okay, one more thing. The beam span, let's say this is my column. Now in which direction beam will bend? Along which direction beam will bend? So beam span will be this. Do we agree with this statement? This is my beam span because these were my columns. Hello. So beam is bending along this span. Do we agree? So this type of beam becomes a composite beam with ribs that are perpendicular to beam span or ribs that are along the beam span. What do you have to say? In this composite beam that I have drawn, the ribs are perpendicular to beam span or parallel to beam span. So this is a composite beams with ribs of deck slab perpendicular to beam span. Anyone having any confusion, just tell me quickly. Okay. Suppose I were to draw a sectional view over here. Suppose I were to draw a sectional view over here. How would this sectional view look like? Suppose let's call it a section XX. If someone is able to imagine, I hope someone is able to imagine this section. So this will look like something like this. Let's say this was an I section that we were using. So this is the I section geometry that I am drawing. If this span of the beam was 10 meters or whatever, 8 meters, then this length of the beam is 8 meters. Are you with me? And how would the deck slab look like? So deck slab would look on top of this like this. Okay, clear? So the ribs of deck slab are perpendicular to beam span. And then of course on top of it we will do the concreting later on. So on top of it we will do the concreting. Very good. So this type of composite beam becomes a deck slab. Sorry, this type of composite beams becomes a beam with ribs of deck slab perpendicular to the beam span. If I were to have a beam over here, let's say connected to the trough of the trough of the deck sheet. Suppose I was to have a beam over here which was connected to the trough of the deck sheet. This pink line that I'm drawing. So this was one beam, this was one beam, and it was connected to the trough of the deck sheet. And suppose I were to draw this section BB, how this section would look like? This section would look something like this. Let me draw it over here. That this would be the beam cross section that you will see. And this time the deck slab would look something like this on the top. So I'm not drawing the entire width of deck slab over here. I'm just drawing a representative width like this. Is it clear? Are we clear with this? Okay, it's clear to Oppo also. Good. Please, Oppo, please join with your full name. I am unable to identify you. Just leave the meeting. Okay, it is Rajen ji. Good, good. I hope it's clear. Yeah. So this section BB is a type of beam where the ribs are parallel to the beam span. Do you understand? Because for this beam, the beam span will be in this direction and the ribs are also in the same direction. This is the span of the beam and the ribs are also parallel to the beam span. So if we were to put some names to these beams, beam number 1, 2, and 3, let's say, are beams where the ribs of the deck slab are perpendicular to the beam span. Just say yes or no if you agree. Beams number 1, 2, 3 are the beams where the ribs of the deck span are perpendicular to the span of the beam. Clear? And beam number 4 and 5 are the beams because the beam span was also in this direction. Because this 4 and 5 beam was, let's say, resting on beam 1 and 2. So for beams number 4 and 5, the ribs are parallel to the beam span. Clear? Yes. So these are the two more types of beams that we want to understand and that we would like to discuss. Now, in this image, if you were to tell me, very interesting work going on. So if you were to tell me, if I ask you this beam, now in this image, you can clearly see the deck slab, you can see the concrete topping, and now you can see two beams. If I were to ask you, this is beam number one and beam number two. Now, beam number one, the beam span or the ribs of deck slab are along the beam span or perpendicular to the beam span. For beam number one that I have put on the image, the ribs of deck slab are parallel or perpendicular, are along or parallel to the beam span. Clear? Very good. And for beam number two, the ribs of deck slab are, complete the sentence, are perpendicular beam span. Very good. So this distinction is clear to all of you? Nice. So these were the two remaining types that I wanted to discuss. So composite beams with solid slab. Now we understand composite beams with deck slab where the ribs are parallel to the beam span, and then composite beam with deck slab where ribs are perpendicular to beam span. There will be differences in their design. There will be differences in the design of the composite beam when the ribs are parallel and when the ribs are perpendicular. We will see all these things, and we also understand the composite beams with solid slab. The good part is that the IS code in depth covers all these three conditions. So we will discuss these three conditions in detail. IS11384 does not cover these two conditions directly, the encased and the infilled beams, for which we will use some jugaad work to discuss. But we will discuss all these types. We will make Excel sheets. In fact, our Excel sheets are also ready that we will be using in this course for all these types of beams. Any confusion question you want to ask related to composite beams till now? I have just introduced the structural system to you right now. Okay. Any question, confusion? Okay. Now to connect, so till now we have discussed two elements. One was your composite beam, sorry, one was your structural steel beam, and the other was your slab. Now, especially in these cases, this is the structural steel beam, and this is my slab. Here I have my beam, steel beam. This is my deck slab, and this is concrete. Now to connect them together to generate the composite action, I'll be discussing in detail about the composite action later on. But right now, I am just asking a simple question. I want to ensure that a structural steel beam and an RCC slab or a structural steel beam with metal deck and RCC topping should act as a single unit. So to enable them to act as a single unit, what do? We put something what is called as a shear connector. Clear? So this is the next structural system that we need to understand. So this is a typical image of shear connector. Can you see this shear connector, please? Hello. Can you see this shear connector? Simply what we have done, this was my, again, these images have been taken from the internet. This is my top flange. On top of it, I have put a connector. Now on top of it, I will either put my solid slab. Yeah, in this case, of course, I'll put my solid slab. So I'll have my solid slab and do the concreting work. So once I do my concreting, the concrete slab and the steel beam will act as a composite unit because of the presence of these shear connectors. Are you clear with this statement? So to ensure composite action, the thing that we require is the shear connector, very important thing to ensure composite action. What do I mean by composite action? I'll discuss later. To ensure composite action, we put shear connectors. Now, those shear connectors may be of different types. You may use what is called as a headed stud connector. Stud means this is like a bolt. Headed means because this has a head on top of it. So this we call as a headed stud type shear connector. We may use other structural shapes also. For example, in the image on your right side, there is this beam. On top of it, you are seeing a different element being used. What is this type of element that you see? What can you find out? Hello. So this is a channel type, as Yogita ji is saying, channel type connector. So you may use this type of a connector, steel channel being used as a shear connector, or you may come up with other structural steel shapes also. Instead of channel, some people use some bars which they bend as a chair type of a thing, and then they use it as a shear connector along the length of the beam. They put this type of a shear connector. So you can come up with any variation, any structural shape, and use it as a shear connector. The basic fundamental of shear connector is that it should ensure that the composite action sets in between the RCC and steel. That is the basic purpose of using a shear connector. So in our code, we have been given the design processes for different shear connectors, the stud type shear connector, or using any other structural steel section as a shear connector has been covered in the code, and which we will discuss. So this is the next structural system shear connectors that we need to understand and that we will be covering in the course. Mr. Haseen is asking spacing of beam, how much we keep along the span. Oh, don't worry, we will cover these things later, not today. I'm just introducing you to the different names right now. Okay. So these are couple of more images. Just hold on, I'll be back. Yes, is my voice audible? So these are a couple of more images that you can see. Headed shear connector on composite slab. Okay, headed shear connector on composite slab. This is the headed connectors. Again, another image where you see a different composite deck profile with headed connector. All these things we will cover in great detail, don't worry. I am just introducing you the names today through images. Then another image I would like to show you, very interesting. Yeah, see this image. Mr. Rajan, you can see this image now. So what's happening in this? I don't know if you're able to make out from this image. Can you see the ribs of the deck slab? So you see a deck sheet in this image. This is the deck sheet. This has been laid. Yeah, this has been laid over. Now you can see the underside of the above floor. These are the beams. These are your main beams, correct? These are all main beams. And I mean below, in the below image, actually this is your main beam, which you cannot see right now. Okay, that I'm putting in black mark. This is your main beam. Are you able to understand what I'm saying? Your spanning of the profile deck will be along the blue line or along the green line. What do you think? The metal deck will span along the blue line or along the green line? This is a question. So the metal deck will span, as Mr. Haseen is saying, as many of you have said, along the green line, correct? Because metal decks will span along the ribs. You can, I think, clearly see the ribs from here image. The ribs are clearly visible, and these are the rib lines. Okay, so this is the spanning of your metal deck. At the bottom side also you can see, in fact, this is the spanning of your metal deck. Now if I ask you this beam that I'm putting as number one, these beams that you see, these are having ribs perpendicular to the beam span or parallel to the beam span. So for these main beams that you see, the ribs of deck slab are perpendicular to the span of the beam, correct? And I think now this is all clear. So for these main beams, the ribs of the deck slab are perpendicular to the main span. Good. There are some secondary beams also you can see. I don't know if you can make that out. I will show you, try to show it in pink colors. Can you see these secondary beams? Yeah. So these secondary beams I'm showing you in pink color. For these pink color beams, the ribs of deck slab are parallel or perpendicular. So for these pink color beams, the ribs of deck slab are parallel to the beam span. Very good. Excellent. What else can you see in the image? You can see stud connectors, stud types connectors put over here. Their spacing, all the criteria we will discuss in detail. Don't worry. You will be able to calculate the numbers required and all those things we will discuss. Manually also, we will see in ETABS also. All those things will happen later. Right now, today, we are just identifying the different systems. So you can see the stud connectors. You can see the deck slab, profile deck slab. You can see the beams. Now on top of it, there will be concreting that will be done later on. Okay. There will be concreting that will be done later on. Do you see any props? Do you see any scaffolding? So you don't see any scaffolding. Okay. You don't see any scaffolding. So there is no scaffolding that has been installed. No formwork required because the deck slab, this profile deck sheet is itself acting as a formwork, and it is also acting as a bottom reinforcement, tension reinforcement. Okay. So now you will do the concreting, and once the concrete hardens, then it will act as a composite system. Clear to everyone? Yeah. Okay. Just one point I would like to tell you. Just one observation over here. Can you see some slots cut over here in the beam? I don't see if you are able to identify from this image. Are you able to see some slots cut in the web of the beam? Yeah. What is the purpose? Can someone just tell me the purpose of cutting slots in the beam in the web portion? For services. Good. Good. as Mr. Haseen and Siddhakal are saying, that these are for service lines to go through. Okay, so you can then easily put your, let's say, if at all you wanted to put a false ceiling, you can put your false ceiling right at the beam bottom flange. And for all the service lines, anyway, because you had this depth occupied by the beam, you just want to use the same depth within which you want to put your service lines. It may be your firefighting or air conditioning ducts or electrical lines or whatever. So those you can take through these sleeves that you have provided in your steel beam. Okay. One more thing that I would like to tell you, in case of solid slabs, when you are putting stud connectors, how do you do it? First, you will put the stud connector like this. Then you will put the formwork for the solid slab, and then you will do the concreting. Understood? I'm saying in case of solid slab, first you will connect the stud connectors on the flange of the whichever connector you are putting. You will first connect it to the steel flange, beam flange. Then you will put whatever your formwork, etc., and then you will do the concreting. Clear? Okay. In the case of metal decks, what do you do? In the case of metal decks, you will put the beam, you will put your beam, then you will put your deck slab also. I am showing you a case where the deck slab ribs are parallel to the beam span. So then you will put your deck slab also, and through the deck slab you will put these connectors. Is it clear? Is the sequence understood? In case of solid slab, you are putting the connectors first, then you are putting your formwork, then you are going to top it up with RCC topping. In case of metal decks profile, you will put your steel beam, you will lay down your metal profile, metal deck, and then from the top you will put these connectors. Okay. So here you see these stud connectors are pre-welded or pre-connected to the steel flange. So these are examples where you are going to put a solid slab on top of it. This is on your right side. This is a typical example of a bridge deck. Okay, I guess this is a bridge deck or some sort of a bridging structure that is being made over here. So in bridges, it's quite common that you will first put the connectors and then you will put a solid slab. While in this case, first they have, this is a image of metal deck profile. So here they have put the beam, then they have laid down the steel deck, metal deck, and now from the top they will put the connectors. Yeah, connectors will be welded to the steel flange through the metal deck. Am I clear with this? This sequence is understood? Good. So these are the shear connectors which we will discuss later in the course. Then of course this is the composite slab which we will in detail discuss. So there are different profiles. This is called as an open profile where you see an open trapezoidal shape like this. So you took a plate and then you passed it through rollers to get this kind of a profile shape. So basically starting point will be, let's say this is, let's say this is 1 mm thick plate. So starting will be that you will have a, please understand, starting point is that you have, let's say, a 1200 mm wide I'm just taking this as a random number right now. You have a 1200 mm wide, 1 mm thick plate. Now you pass it through rollers, and by passing it through rollers, you form it into this kind of a shape. Is it clear? I hope this is clear now. Okay. And the final width that you get, let's say you got a 900 mm width. Why did your width reduce? Because of course it was utilized in these crest and troughs. So that means if you were to add up the total length, it will be larger. So let's say it came out to be 1200, and after forming, the plan width remained whatever, 900 or 1 meter or whatever. Understood? Clear? So just one more point over here. Yeah. So here that means what you see is that these deck slabs that you get, these you get in some standardized width. So let's say it will be a 1 meter width. All these are 1 meter width panels, and then you overlap it just like you do your roof sheeting. Have you seen corrugated metal sheets? Sorry, corrugated roof sheets, galvanized aluminum roof sheets. Those also come. Those are also profile sheets, if you have observed. Yeah, those are typically 0.5 mm thick profile sheet, and those have corrugations, and then you overlap it where it ends. So typically they come in whatever is the width, 1.2 meters or 1 meter, and then you overlap it. So similarly over here, these deck sheets will come in standard width, and then you will overlap it and then lay it down. Understood? Okay. So from a larger total width of the plate, you get this kind of a form shape. Usually we will call this as a open profile. These are called as the embossments. I am not sure if you can see. Can you see some patterns marked over here on the deck slab side wall? Can you see these patterns? Yeah, these are called as embossments. And then these embossments have certain pitch. These embossments will have certain pitch. We will discuss all these things later. This is a dimple that has been provided over here in the shape. Okay, this is a dimple that has been provided in the shape. This will act as a rib. This will also act as a rib. It helps you to prevent the local buckling of these thin plates. These things we will discuss today. We are just introducing different topics to you. So these are the dimples or ribs. These are running along the length. You can, I don't know if you're able to make out, but this is a rib that is running along. Yeah, you see, this is that rib. Okay. Then if you are able to see, there is a rib at the trough also. This is that rib. Clear? So you make this shape. This typically is called as a open profile. Why are we making these ribs and embossments? I'll discuss it later. But anyone could give me a quick answer? Just one line answer if someone could give me. Why are we making these dimples and these embossments and all these things? Why we are doing this? Later on, we are going to put concrete over here. Yes, one line answer, anyone, if they want to give. Otherwise, anyway, we are going to discuss these things later on. Rajenji is saying to increase the Z. Yeah, but this will very marginally increase Z. Very margin. What is this? This is around 10 mm, not even 10 mm, 2 mm, 3 mm, 5 mm. So it does increase Z, but that is very, very negligible. Yogita ji is saying better composite action. Correct. So, so basically in composite slab, we do not provide shear connectors. Okay. To attain composite action between the concrete and the metal deck, we rely on these embossments, these patterns, the very shape of the composite metal deck, sorry, the very shape of the metal deck. We rely on all these things to help us achieve composite action. Are we clear? So these provide you the frictional interlock. These embossments and these dimples and these ribs and all these things help you to provide frictional interlock between the concrete and metal deck. So they act as shear connectors. Okay. And then these are proprietary products that are made by your manufacturers. So this is a deck slab manufactured by Tata Comfloor. Comfloor is their brand name for deck sheets. And this is 46. 46 is the thickness. Okay. And on top of it, there will be concreting that will be done later on. Is this clear so far? Good. Now there was this question being asked by Mr. Hasim that how or what will happen at the overlap. So although I'll cover these points later on, but just for your understanding, what will happen at the overlap? Can you see this part? So this part basically will go over here for the next sheet, and this will perfectly match, and then it will continue like this. Are you clear? Did you understand what I'm saying? This part you see, so this part will be overlapped with the next item. For example, this shape that you see now, this will get overlapped over here for the next width. So it will be like a male female overlapping like this. So this will happen. Is this clear? So deliberately they make the shapes like this that they are easily overlapped. Good. So this is your profile, open profile. Then this was another shape. This is a profile manufactured by Tata Comfloor. The brand name is Comfloor. Section type is 51. This shape is called as the re-entrant corner. So this thing that is coming inside, this is called as a re-entrant profile. Can anyone tell me why this shape has been made? Why this shape has been made? Why or how this shape is different from the open profile that we were seeing earlier? This was an open profile. This is a re-entrant profile. Why this shape and how it will be beneficial? Anyone? So again, you can see embossments. You can see these embossment patterns. How this shape will help you? Yes, please. So we will do concreting over it. We will do concrete topping over it. How this shape will be better than the earlier shape that I showed you. If you knew nothing about the concept, and if I just asked that out of these two shapes, which of the shape will provide better composite action between RCC and metal profile? Let's say you did not understand or you did not know anything about this, but still just out of your intuition, if I asked you that this shape that I'm showing you, re-entrant profile, and I had an open profile, which of these two profile types will give you a better composite action between concrete and the metal deck? Tell me. So I think most of you would agree that because of this re-entrant profile, where these things are coming inside the concrete, this will give you a better composite action. Yeah. So the purpose of making re-entrant profiles is to have a better composite action. Are we clear with this? So here I am able to get the composite action due to what is called as the mechanical interlock. Of course, I am getting mechanical interlock in the earlier case also, but here I am able to get better mechanical interlock. So this shape is giving me good mechanical interlock, plus the dimples and these embossments and these things give me frictional interlock. So there are two terms which we use, frictional interlock and mechanical interlock. So these reentrant profiles give me good mechanical interlock, embossments and ribs and all these things help me to get the frictional interlock. Again, this shape, this thing that is coming inside the concrete, that gives me good mechanical interlock, and the ribs and dimples and embossments give me frictional interlock. But in reentrant profiles, I get better mechanical interlock than your open profile. So these are another type of profiles that you see. Again, this is a product from Tata Comfloor. You can see the cross-sectional view over here. And for overlap, how will the overlap happen? So you can see, now I think you can understand that overlap will happen over here, whereby this thing will go over here. Is it clear, Mr. Asim? Hello. Like this, and this will continue. Clear? So deliberately they make, and over here, the overlap, this thing will come here when you have to make the overlapping. So deliberately the shape is made such that easy overlaps are possible. Clear? So this is the composite profiled metal deck slab. This also we'll be discussing. Then we will discuss composite columns. I think today we will stop over here. Tomorrow in the next session we will see, we will first introduce the different composite columns that we are going to discuss. And then we will begin with the two stages that we need to understand in composite design, and then we'll take up other topics. So I think today we will stop here. This session will be uploaded on our portal after some time. Uh, After a couple of hours, this session will be uploaded. So all of you have been added on the portal learning platform. That is, you can go online and watch that session. You can watch the session live also. You can watch the session on our learning platform. Also, you can do both. Whatever you want, you can do. There is no restriction as such. I hope today's discussion you understood. Today we just introduced few basic terms and few structural systems. All these things we are going to discuss in great detail with detailed manual calculations, with verification on software like ETABS and on Excel sheets. So I'll continue with this in the next session. I'll stop over here for this session. Thank you very much and bye bye. Bye.